Welcome to the Wine Math series. My name is Maureen Moroney, and in this video we'll be going through some calculations for yeast counting with a hemocytometer. If you would like to skip the detailed explanation and head straight to an example, you can use the timestamps in the description to find the section of the video you're most interested in. Let's get started. To give us an idea of what numbers of yeast cells are typical in wine, it's important to consider the stage of the winemaking process. Yeast cells are microscopic, so we're usually talking about very high numbers, up in the millions of cells per milliliter. With numbers that big, you might sometimes see exponential notation used. What that means is that instead of writing out all those zeros, we keep the first digit in the ones place and then write times 10 to some exponent, where the exponent indicates the number of places we've moved the decimal. Multiplying by 10 to the first means multiplying by 10. Multiplying by 10 to the second means multiplying by 100. Multiplying by 10 to the third means multiplying by 1,000, and so on. If that doesn't make sense, it's okay. I'll show you an example on the first one. So at inoculation, most commercial yeasts will recommend an inoculation rate that will result in 5 times 10 to the 6th cells per milliliter. And what that means is 5 million cells per milliliter in the must. So 5 times 10 to the 6th means taking the decimal in 5.0 and moving it 6 places to the right. So that would mean 1, 2, 3, 4, 5, 6, which we have to add then all those zeros, and that would be 5 million, okay? And then during fermentation, around the peak of fermentation, we typically see something like 1 times 10 to the 8th viable yeast cells per mil. So we're talking about something like 100 million cells per mil. And then post-fermentation, let's say after the wine has been racked and maybe it's aging in barrels or maybe it's been bottled without filtration. So at that point, it's typical to see somewhere around 10 to the 3rd or 10 to the 4th cells per milliliter. But at this stage, there's quite a bit of variation. Of course, if you're post-fermentation and you've gone through sterile filtration, all of those yeast cells at that point should be removed, so that's a different thing. But prior to any filtration step, this is the kind of range that we're talking about. So today we're going to look at one way of actually quantifying the number of yeast cells per milliliter of wine. This requires a microscope and a special slide called a hemocytometer. It was originally developed to count red blood cells, so hemo equals blood, cyto equals cells, and meter equals count or counting. So the way this works is that there is a well built into a special microscope slide, and the sample is placed into the well. The well has a precise depth of 0.1 millimeters, and it has a tiny grid etched into it so that you can see the grid when you look at your sample under the microscope. The grid has squares with specific side lengths, as shown here. Let's zoom in on one of these sections in the next slide. There are specific rules for counting which are designed to avoid over or undercounting things like budding cells or cells on the border between squares. I'm not going to get into detail about the rules here, but I will point out that it's best to move methodically so you don't lose your place or skip or double count any cells. It's also a good idea to choose a few different areas of the grid of the same size and then average them before doing the next step of the calculations. In this image, in case you can't read it clearly, the full length side of this section with the triple outline is labeled as 0.2 millimeters. And as you can see, there are 16 smaller squares inside it. Very briefly, the conventions for counting are: count the 16 small squares in an intermediate square, the one that's bounded by the triple line. Count cells touching the left and the top boundaries, but exclude cells touching the bottom and the right. If there are budding cells, count the daughter cell only if it's at least half the size of the mother cell. Once you know how many cells, on average, were in a section of a certain size, you have to figure out the volume of sample that was in that section. So let's say that you counted an average of 2 yeast cells within a section that's 0.2 millimeters by 0.2 millimeters. This is just like any other volume calculation where you know the length, width, and depth. In this case, the depth is always 0.1 millimeters because that's the depth of the counting chamber. The length and width will depend on which size square you counted. It's very common to count the 0.2 millimeter by 0.2 millimeter squares as shown on the previous slide, so we'll use those dimensions for our calculations. In order to get the volume, we multiply the length times the width times the depth. 0.2 times 0.2 times 0.1 works out to 0.004, and our units are millimeters times millimeters times millimeters, which works out to cubic millimeters. This means we have 2 cells per 0.004 cubic millimeters. So how do we convert that to milliliters? Well, one of the nice things about the metric system is that 1 milliliter equals 1 cubic centimeter. Even just visually, you can kind of see that if you had a cube where each side was 1 centimeter in length, it would take up a milliliter's worth of space. The tricky part here is that even though there are 10 millimeters per centimeter, there are 1,000 cubic millimeters per cubic centimeters. So in order to get to cubic centimeters, also known as milliliters, we have to do some more math. 0.004 cubic millimeters times 1 cubic centimeter over 1,000 cubic millimeters equals 0.00004 cubic centimeters, or 4 to the minus 1, 2, 3, 4, 5, 6 And remember that cubic centimeters are the same as milliliters. So we have 2 cells per 0.000004 milliliters, which works out to 500,000 cells per milliliter. One extra layer to this is if you use methylene blue for viability staining. I won't go into the details of doing that staining here, but the idea is that you add methylene blue to your sample and mix them together, and dead yeast cells turn blue while living yeast cells stay colorless. So let's say you mix 1 drop of your sample with 1 drop of the methylene blue stain, then you put that in your hemocytometer. You've now made a dilution of your sample. You have the same number of cells in twice the total volume of liquid that you did in your original sample. This means that under the microscope, you're seeing half as many cells in the same amount of volume. So whatever cell count you get for the diluted sample, you have to double it in order to reflect the count in your original sample. I actually recommend doing your counts unstained because the methylene blue is toxic to the yeast cells. So it's a bit time sensitive, as over time more will die and turn blue. So you can do your counts without stain and without worrying about the dilution factor, and then afterwards you can go back and do staining to estimate what percentage of the cells are viable. So to summarize all that, there's a formula shown here which includes all the pieces we just worked through. This first fraction shows the average cells per whatever area you counted. The volume of that area is shown here. And the dilution factor is included, which would just be a factor of 1 if you didn't dilute the sample at all by staining or anything like that. One of the hard parts about doing these kinds of calculations is just wrapping your head around much smaller volumes and much larger numbers of cells than we're used to thinking about. But to put it into some perspective, we can think about a drop of liquid. When we fill the hemocytometer, we put 1 drop into the well, and most of it actually overflows out of the counting chamber. The part we see in the grid is a small fraction of that drop. Now, consider that in 1 milliliter, there are 20 drops. So 1 drop equals 0.05 milliliters. This means that if you're below a certain number of cells per mil, you are unlikely to actually see any in the hemocytometer, even if you look at the entire grid zoomed all the way out. The largest outside square of the grid is 3 millimeters by 3 millimeters, which means the volume is 0.9 cubic millimeters, or 0.0009 milliliters. If we think about 1 cell in that volume, that would work out to 1,111 cells per mil. This is important to keep in mind because not seeing yeast in the hemocytometer doesn't necessarily mean there aren't any yeast cells in the wine. However, using a hemocytometer is a quick and inexpensive first step in helping to monitor yeast populations. Thanks for watching this wine math video. If you have any questions regarding the math or the general wine topic covered, feel free to reach out to us at wine@iastate.edu. Check out the other wine math videos to improve your math skills in the cellar. Cheers!